We've seen that simple linear regression provides us a great tool for understanding the relationship between two numeric variables. For instance, if we were working at Kroger, we might be interested in making a prediction in terms of how much money people are spending per year at Kroger based on their yearly income. So simple linear regression provides us an equation to make a prediction and even to come up with 95% confidence in prediction intervals for a particular household that has an income or the average amount spent over all households that share the same common income of, say, $50,000. The simple linear regression also allows us to compare the expected amount spent across different households. Two households that differ in household income by, let's say, $1,000 per year might be expected to differ in terms of their spending at Kroger by maybe $3.40 on average. But you know what's better than predicting the household expenditure from one variable?
Predicting it from two variables.
Predicting it from three variables.
Predicting it from four variables. Predicting it from five variables.
Bananas. Peanut butter.
And that's going to be the job of multiple linear regression, where we have multiple potential predictors of a quantity like household expenditure at Kroger, and we want to utilize all of the information that's available to us. So if we want to predict the household expenditure at Kroger, we'd love to use not only their income and maybe the distance that a household lives from the nearest Kroger, the number of kids, the number of pets in that household, the number of cars that belong to that household, etc. There might be multiple viable predictors that we want to use in order to come up with the best predictions possible. Now, the multiple regression model allows us to leverage multiple sources of information to come up with a better prediction than any one of those predictors could have given us. So in the model, we're going to stick to predicting a Y variable. This might be the amount of money that someone spends at Kroger. This might be someone's salary. This might be the length of time someone spends on a website. And as the name suggests, we're going to have multiple X variables that serve as predictors. X1 is going to be our first predictor variable, maybe someone's income. X2 is going to be the second predictor variable, maybe the number of kids in the household. X3, X4, etc., are going to be other predictors that we might use. We're going to say that we have k total predictor variables, x1 through xk, and we see the form of the model allows us to piece together the predicted value of y as more or less a weighted sum of the predictor variables, with each of the predictor variables getting a weight, the coefficient, beta 1, beta 2, beta 3, etc. Along with that, we add in an intercept, and since we know that individual values of y are going to deviate from the overall average, we're going to throw in a disturbance, an epsilon term, that allows us to capture the random amount by which individuals differ either above or below the overall average value of y at that particular combination of x values. So let's use some multiple linear regression to do some predictive analytics. And just like with simple linear regression, our predictions are going to come in two flavors. We might be interested in predicting the average value of y among all individuals in the population with a common set of x variables. Or we might be interested in predicting a particular individual's value of y who has a particular set of predictor variables. Let's see how this works. So the example that I want to look at involves predicting the tip percentage left on a bill based on the bill amount and the party size. But first, let me read in this first chunk of code that's creating some additional data sets that we'll use a bit later, and then I'll scroll down to where we fit a multiple regression model to try to figure out the tip percentage. So I'll load in the library reg class, and I'll load in the ex2.tips data frame because this data lets us do the analysis. We have a column for the tip percentage left on a bill. We have information on the bill in US dollars, and we have information on the party size. So how do we set up a regression model to use multiple predictors when doing the predictions? Well, it's a pretty simple extension of the simple linear regression framework. So what we'll do is we'll create an object, m.tips, that's going to be the result of running the lm command, lm for linear model, just like with simple linear regression. And the setup is fairly similar. So the first argument is going to be a formula that tells R what we're predicting and then what we're using to make those predictions. Our y variable in this case, what we're predicting is tip.percentage. So we'll put that to the left-hand side of the twiddle to let R know that that's our quantity of interest. And then on the right-hand side of the twiddle, that's our place to put all of the predictor variables, the columns that we want to use in the data frame that are to serve as predictors. So we'll separate these by plus signs. So we're predicting the tip percentage from the bill and the size of the party. Since both these columns live in the ex2.tips data frame, we'll add in the data argument as well. So when we run this, we're able to get a summary. And just like how we translated the output of summary into a regression equation with simple linear regression, we can do something very similar. So the intercept is clearly labeled for us, $19.90. Well, it's tip percentages, so 19.9%. Then minus 0.27 times the bill amount, then plus 0.6 times the size of the party. We'll talk about how to interpret those coefficients a little bit later on, but we can immediately use this regression equation to make predictions. What if a bill was $20 and the party size was 2? Well, what would we predict the tip percentage left on that bill? All we have to do is plug in the relevant predictors into the equation. So we start out with the intercept, the 19.9%, that's kind of our baseline, and then we adjust it based on the bill size and the party size. We take the coefficient of bill size, we multiply it by the bill amount, $20, and then we add that to the coefficient of party size times our party size of 2. And once we get that out, we predict that the tip percentage left is going to be $15.68%. Now, remember, there's two types of predictions that we do in analytics. We might be predicting the overall average value of y among all individuals in the population that share that particular combination of x's, or we might be trying to predict an individual's value of y at a particular combination of x. So in this case, we can run both of these predictions by doing the predict command. So just like before, what we'll do is we'll set up a data frame called to.predict that tells us what value of bill and what value of party size we want to be getting estimates for. So in the data frame, I'm going to match up the column name that I used as a predictor as the column name in to.predict, and I'll give it a vector of values for bill amounts that I want to be predicting at. So let's make a prediction at bill sizes of $20 and $60. And then we'll add in a second column corresponding to the second predictor. That name will match up with the name of the column in our data frame that we used to build the model. Size of party equals 2 and 3. So we're going to make predictions for bills of size 20 from parties of size 2 and bills of size 60 from parties of size 3. So we can confirm that the to.predict data frame contains the combinations that we're interested in, and then we can just throw this through the predict function. The name of our model, the new data equals to.predict, and then we'll add the interval argument that specifies what kind of interval we want out for our predictions. The confidence interval is going to give us a 95% confidence interval for the average tip amount among all parties of size 2 that spend $20 and all parties of size 3 that spend $60. The interval equals prediction is going to be a 95% prediction interval for some particular party that shows up and has 2 people in it and they spend $20, or some party shows up in it and there's 3 people in it and they spend $60. So let's look at both. So our 95% confidence interval for when the bill is $20 and the party is size 2 is as follows. Our best guess is that the tip percentage is going to be 15.68%, and we're 95% confident that the average tip percentage among all parties of size 2 that spend $20 is going to be somewhere between 14.77% and 16.6%. So is the actual average tip percentage in there for these types of parties? Well, we don't know. That's exactly what we're trying to estimate. We know that a 95% confidence interval, the procedure we're using to build it, gets it right, covers the true value of the average 95% of the time. Now, normally in analytics, we're more interested in predicting individual amounts. So a party just came in and there's 2 people in that party. And they just ordered some food, so we know their bill is going to be 20. What do we predict for that particular party's tip percentage? Well, if we have the interval equals prediction argument, that's going to come up with a 95% prediction interval. So the point estimate, our best guess, is still exactly the same, 15.68% left on that bill. And now we can say that there's a 95% chance that the tip percentage will be between 4.3 and 27.1 percentage points. You'll notice that the model kind of breaks down and starts giving nonsensical predictions for the other combination, bills of $60 from parties of size 3, because it contains negative values inside the 95% prediction interval. The model simply doesn't know that the lowest possible tip percentage is 0. That's going to be a shortcoming of our model. We know all models are wrong. Some are useful. This prediction interval isn't the most useful for that particular type of combination. So, predictive analytics with multiple regression, pretty easy to do. Of course, you'll have to make sure that the regression model is a reasonable reflection of reality, and we'll talk about how we check the assumptions of a multiple regression model later on. But for now, if everything is peachy keen, then it's pretty easy to do predictive analytics with multiple linear regression. Now, multiple regression can also be used for descriptive analytics to try to understand what is the relationship between our y variable and our predictor variables. But it's sufficiently more complicated that even people that have been doing regression for years very often misinterpret the coefficients of a multiple linear regression model. So we want to make sure by the time you're done with this class that you are experts at talking about exactly what the coefficients of a multiple linear regression model mean and what they don't mean. So first, very quick review about how we interpret the coefficient in a simple linear regression when we just have one predictor variable. So that's what we call the slope, or beta 1, of our model, and we've had a lot of practice interpreting this. We envision two individuals, they differ in x by 1 unit, and so the slope, beta 1, tells us the expected difference in y between them. So if that coefficient is positive, the individual with the larger value of x is expected to have the larger value of y, and if the coefficient is negative, the individual with the smaller value of x is expected to have the larger value of y. Now, simple linear regression has a pretty severe shortcoming if there are multiple different characteristics that are good predictors of y. So sometimes you can't actually put too much weight in terms of the interpretation of the coefficient when there's more complexity involved in the relationship. So what I want to do is I want to illustrate this with a particular example. Let's imagine that someone's grade in a class is tied into their score on the assignments and their score based on their attendance. And it's weighted in terms of 80% assignments and 20% attendance here. Now, here's a little bit of a twist. The students act in a very particular way. If the student feels very confident in their ability to do the work, they're doing well on their assignments, they tend to not show up to class all that often, so their attendance score is fairly low. And vice versa, the students that feel like they're struggling, not doing the best on their assignments, are showing up a bit more often because the class sessions seem to help, seem to boost their scores from where they would be if they weren't attending. So let's check out a simple linear regression model predicting someone's grade based on their assignments, based on this data that was created in that very first R chunk. So first thing I'm going to do is I'm just going to create a scatter plot that's going to show us the relationship between the course grade and their assignment grade. And I'm going to color code this by the two types of students that we know live in this data set, the ones that are excelling in the class and the ones that are struggling. So if we look at this scatter plot, it looks like we have two separate streams of points, and that's true because these two different types of students are well differentiated from each other. We can fit a regression model and add that line to it. This would be our overall linear regression. But let's check out to see if we can capture the weight that's been assigned to the assignment scores when determining the course grade. If we get a summary of our regression model, we find that the estimated coefficient of assignments, that estimated slope, is 0.583. And if we get a 95% confidence interval for that, we're 95% confident that the true slope is somewhere between 0.52 and 0.65 here. But that's wrong, because we know that by design, the way the grade is set up, the assignments should have a slope of 0.8, because we take the assignment score and multiply by 0.8 to get someone's grade. So regression is kind of missing the actual coefficient in this case. And the news is even worse if we go and look at the relationship between grade and attendance. If we make the scatter plot here, we have the two groups of students. Now, if we go fit a linear regression model, add it to the scatter plot, and then look at a summary, we find something a bit puzzling. We find that the estimated coefficient of attendance is negative here, implying that students that tend to attend more often have a lower grade than students that attend less often. And in fact, if we get a 95% confidence interval, we find that we're 95% confident that really the true slope is negative. All the values in this interval are negative, implying that the more students attend, the less they typically do well in the course overall. And we know that that's wrong as well because the course grade is weighted based on their attendance. In fact, the weight assigned to it is 0.2. So here, the simple linear regression is kind of missing the truth here. It's missing the full picture of how these variables are related. And that's because when we fit a simple linear regression, we're really only accounting for one source of variation in our y variable. So yes, someone's grade varies based on their assignments. Yes, someone's grade varies based on their attendance. But if we fit a model that just predicts grade from one of them, but not the other, we're leaving out a very key component of how individuals' grades vary. And so when we do have these extra sources of variation that aren't inside the model, we call them lurking variables, because it's another reason we expect individuals' y values to vary. And if we're not putting that in the model, we're leaving ourselves open to potentially misleading coefficients. These lurking variables can profoundly influence the impression of the relationship between y and x, leaving us kind of scratching our heads in some cases, like how we saw the coefficient of attendance was negative when determining the grade of an individual. So when we go back and look at the summary of the grades versus assignments, we would say that, okay, two students whose assignment grade differs by 1 are expected to differ in course grade by 0.58. But, when we say that they differ in assignment grade by 1, they're also potentially differing in other substantial and important ways. We don't have a comment about how they're differing in terms of their attendance, and because attendance is also tied into someone's final grade, we're missing out on that key part of the story. What we're going to do is we're going to call the attendance a lurking variable in this case. So we're predicting grade from assignments, but attendance also influences someone's grade. It's a lurking variable because it's another reason that these students might vary from one another when they do differ in terms of assignment by, say, 1 percentage point. But our model's not accounting for that, and when we don't capture all the sources of variation, the coefficients of our model can turn out to be, pretty misleading. The good news is, though, is that that's the purpose of multiple regression. Multiple regression is going to allow us to account for lurking variables, to account for all the potential sources of variation in the individual's y values, as long as we can identify all the reasons why individuals might have different y values here. So let's try to predict someone's course grade from both the assignment score and their attendance score. If we predict using both these variables, the only two sources of variation among people's grade, what we find is that we recover those coefficients exactly. The weight given to assignments was 0.8, the weight given to attendance was 0.2, and so we're discovering the true form of the relationship once we've accounted for all of the sources of variation in individuals' course grades here. So multiple linear regression is a fantastic tool to really fully study the complex relationships between an individual's y value, like their salary, their amount spent, etc., based on a multitude of potential predictors, a multitude of reasons why they might actually be expected to have different y values. So let's see how the multiple linear regression model does this. How do we interpret the coefficients that come out of a multiple linear regression model? And surprisingly, this is one of the most complex and subtle things in all of analytics. Even people that have been doing regression for years and years still often misinterpret the coefficients of predictors in a multiple linear regression model. And so we want to make sure that by the time you finish this course, you are experts at letting everyone know what a coefficient does and actually doesn't tell you. So here's how we're going to interpret the coefficient of a predictor in a multiple linear regression. We're still going to envision two different individuals, but these individuals are going to be differing in a very specific way. So if we're looking at the coefficient of a predictor, let's call it x, we're going to say that these two individuals differ in x by 1 unit, but otherwise they are identical. Meaning that all of the other predictors we put in the model, those two individuals have identical values for all those other predictors. The only thing they differ is in terms of x, and they differ in terms of x by 1 unit. So when we interpret this coefficient, we envision these two individuals, and we say that two otherwise identical individuals that differ in x by 1 unit are expected to differ in y by whatever that coefficient was. If the coefficient's positive, the individual with the larger value of x is expected to have the larger value of y. If it's negative, the individual with the larger value of x is expected to have the smaller value of y. So the key update in our interpretation is that we're envisioning otherwise identical individuals. They differ in x by 1 unit, but they're the same in terms of all of the other predictors that we have in the regression model. And so this allows us to account for variations in individuals' Y values due to these other factors, because we're kind of holding them constant between these two individuals. So let's get some practice in interpreting the coefficients of a regression model. Here's a different salary dataset that lives in the Reg class package, and this is a real-world dataset that comes from a bank. And let's try to predict the salary from someone's number of years of experience. Now, in this data set, we actually have multiple potential predictors. We have the number of years of education, the number of years of experience, the number of months they've already been working at the company, and also the employee's gender here. What if we just fit a simple linear regression that tried to predict salary from experience? We're kind of leaving out other potential important sources of variation, and we'll see why this matters in a second. So we've loaded up the data, we've fit the simple linear regression model, and let's take a look at the summary. So what we see is that the estimated coefficient of experience is 10.4. However, it's not statistically significant because the p-value is at least 0.05. And so we would say that experience is not a statistically significant predictor of salary. So a little bit weird because you would expect it to be tied in there. But notice what happens when we actually include all potential sources of variation for someone's salary, not only their experience, but then also the length of time they've worked at the company and also the number of years of education. Well, we know that once we account for these other sources of variation, we're going to get a more complete picture of what these relationships look like. And so we will fit the model and get a summary of it. All right. Now the story has changed a little bit. If we look at the coefficient of experience, we find that it's 11.8, and it is also statistically significant. Its p-value is less than 0.05. Much more on that in a later lecture, but we're discovering something actually pretty important. After all, experience does seem to be tied in to someone's salary. A simple linear regression kind of missed that fact because it didn't incorporate other reasons why individual salaries might vary. We didn't have the number of months a person was working at the company. We didn't have the education that they had when they were hired here. By focusing on just experience alone, the variation in salary due to these other factors, the tenure at the company and also the number of years of education, washed out the effect that experience had, leaving us unable to really detect it with just that simple linear regression model. But by throwing in all of the potential sources of variation, education, experience, and months, we have a much clearer picture. So what does this 11.8 really tell us? Well, it tells us that among two otherwise identical individuals, meaning that they have the same years of education, they have the same number of months at that company, among those two otherwise identical individuals that differ in experience by 1 year, we expect their salaries to differ by $11.85, with the person with more experience expected to have the higher salary. Let's do this again, but for the education variable, the coefficient is just about 93. So how do we interpret this? Well, we say, okay, if we can compare two individuals that have the same value of experience, they have the same value of months, doesn't actually matter what those values are, they're just identical. Among those two employees that have the same experience level, that have the same value of months, if they differ in terms of education by 1 year, we expect their salaries to differ by about $93, with the person with more years of education expected to have the higher salary. Let's do another example where we try to predict the tip percentage left on a bill based on the bill amount and the size of the party. So we have an intercept of 19.9%, a coefficient of bill of minus 0.27, and a coefficient of party size of right at about 0.6. So what does this minus 0.27 mean? Well, we start out on our interpretation by saying two otherwise identical parties with respect to the other predictors in the model. So the only other predictor besides bill is party size. So we're assuming that these two parties have the same number of people in it. So two equally sized parties that differ in terms of their bill amount by $1 are expected to differ in their tip percentage by 0.27 percentage points. Since the coefficient is negative, the party that had the higher bill is expected to leave the lower tip percentage. All right, what about the 0.6, the coefficient of size of party? Well, once again, we start out our interpretation. Two otherwise identical parties, meaning they have the same bill amount, identical values for the other predictors in the model. Bill is the only other predictor. So two parties that spend the same amount of money on their bill, when they differ in terms of party size by 1, we expect them to differ in tip percentage by 0.6 percentage points. Since it's positive, the party with the larger number of people in it is expected to have the larger tip percentage. One more data set to practice on. Let's load up the body fat data set that lives in Reg class. And in the body fat data set, we're given someone's body fat percentage, as well as their age, their weight, their height, and then a bunch of physical measurements. So the circumference of their neck, their chest, their abdomen, etc., etc. So let's try to predict the body fat percentage from every predictor we have available to us. Instead of typing out every single column name and separating by pluses, there's a shortcut for that. So body fat twiddle dot means predict body fat from every available predictor in the data frame. So we'll fit that linear regression model and we'll look at a summary of it. A lot of different predictors, a lot of different coefficients. So let's see what we can do with it. So let's look at the coefficient of abdomen. It's about 0.89. What does this tell us? So we start out the interpretation by saying two otherwise identical individuals that differ in abdomen circumference by 1 centimeter are expected to differ in body fat percentage by 0.89 percentage points. Now, by otherwise identical, we mean they have the exact same age, they have the exact same weight, the exact same height, exact same neck circumference, chest circumference, etc., etc. They're identical with respect to all other predictors in the model. And you might be scratching your head or your chin and asking, are individuals like this? Are there two individuals that differ in abdomen size by 1 centimeter, but otherwise have the exact same body proportions, height, weight, and age? Well, maybe there is, maybe there isn't, but that's how we do the interpretation of this coefficient in the multiple linear regression model. We're envisioning two otherwise identical individuals, same body measurements, height, weight, and age, but they differ in terms of their abdomen circumference by 1 centimeter. If that's the case, we would expect them to differ in terms of body fat percentage by 0.89 percentage points. All right, what about the coefficient of weight here? We see that it's negative, minus 0.08. What does that tell us? Well, two otherwise identical individuals that differ in weight by 1 pound are expected to differ in body fat percentage by 0.08 percentage points. Now, since it's negative though, we expect the person with the larger weight to have the smaller body fat percentage. Now, does that sound right to you? It doesn't sound right to me because the way that I know how weight and body fat percentage are related, the more you weigh, typically the more body fat you have. But remember the specifics in terms of how we interpreted this number, because we're envisioning two otherwise identical individuals with respect to all the other predictors in the model. So it's letting us know that these two people that we're comparing that differ in weight by 1 pound, they have the same age, they have the same height, and they have the same circumferences for all of these physical measurements, their neck, their abdomen, their thigh, etc. And so now the coefficient actually makes a bit of sense. If we're comparing two people with the exact same body proportions, but one weighs a bit heavier than the other, well, it stands to reason that that person probably has more muscle mass. Muscle mass weighs more, and so if someone weighs more because of additional muscle mass, they're going to have a smaller body fat percentage. So I think ultimately it really does make sense after all. So once we've come up with our estimated coefficient, the natural question is, okay, well, how far off is our estimated coefficient from the truth? The true coefficient that we would measure if we had a census, data on everyone in the population. We know our guess is a good guess, but it's wrong, but hopefully it's not too wrong here. So this is a word that we've used before. We call this the standard error of our estimated coefficient. The standard error of our estimated coefficient is our best guess for how wrong our guess is. It's the typical difference between our guess and what the true value of the coefficient is if we had a census. So for example, we estimated the coefficient of weight to be minus 0.08. Surely that's wrong, but it's not going to be that wrong. It's only going to be off by a little bit. How far off do we think it is? Well, if we just move our eyes to the right, we get the standard error of our estimated coefficient. So we think our guess of minus 0.08 is off by maybe 0.05 or so. So what I want to do is actually talk about kind of a quirk when it comes to multiple linear regression, and that is that the size of the standard error of our estimated coefficients is actually tied in to the amount of redundancy we have in terms of our predictor variables. So if we think about it, abdomen definitely is related to someone's body fat percentage, but the information about body fat percentage that abdomen contains is likely somewhat redundant with the information that, say, chest circumference has, that neck circumference has as well. As people gain more and more body fat, they kind of gain it all around their body, so all of these measurements are somewhat correlated with one another. People with above average abdomen circumferences are also going to have above average neck circumferences, chest circumferences, thigh circumferences, etc. So if we think about it, the information that abdomen has about someone's body fat percentage is kind of shared by the information that neck circumference, chest circumference has about body fat percentage as well. The information that all of these physical measurements have about body fat percentage are kind of redundant with one another. They're not independent measurements of people's body fat percentage because they're all related. And it turns out that the size of our standard error is tied in to this amount of redundancy. So let me flesh this out. What I want to do is I want to look to see, well, how well can I actually predict abdomen, let's say from the other predictors in the model. So if I go and set up a linear model in LM that says, okay, let's predict abdomen from everything, twiddle dot, but body fat, I can actually do everything but a particular predictor by doing twiddle dot minus the predictor I don't want to use. So if I want to predict abdomen from all of the other x's, which is all the other columns except for body fat, that's my y variable, I can set up the model to be like this. And when I do so, here's what I find. If we look at the r squared of this model, it's letting us know that if we have all of these other physical measurements, that gets us 91.5% of the way there to knowing someone's abdomen circumference. So yeah, while abdomen circumference surely is tied into someone's body fat percentage, the information that abdomen has about body fat percentage is kind of already encoded to some extent, like 91.5% of that information is already encoded by the set of the other physical measurements. And it turns out when there's a lot of redundant information flying around, that's going to degrade the precision of our estimated coefficient. It's going to make the standard error of our coefficient larger than if every predictor variable was independent of one another. Let's see that in action. If we were to look at the model where we just predicted body fat from someone's abdomen circumference, we would estimate the coefficient to be 0.585, basically, give or take maybe 0.03 or so. We think our guess is probably off by maybe 0.026. Now, if I fit the full multiple regression model predicting body fat from everything, look at a summary, and then look at the standard error of my abdomen coefficient, I see that the standard error is quite a bit larger, 0.08 versus the 0.026 when I just had it as a predictor by itself. And so this is a hallmark of a multiple linear regression model. When there is a lot of redundant information flying around among the predictors, the precision of those estimated coefficients gets degraded. The standard errors get quite a bit larger. And that kind of makes sense. If we think back to it, we were a bit puzzled when we were thinking about two individuals that differed in terms of abdomen by 1 centimeter, but were exactly the same in terms of all of these other measurements. That's not really what happens in reality. If they're going to differ in abdomen circumference by 1 centimeter, they're going to differ in terms of all of these other variables by some amount as well. So since the interpretation of a coefficient in a multiple linear regression model puts us in this world where our two individuals differ only in abdomen by 1 centimeter, but are exactly the same in every other regard, it's going to make it really difficult to really disentangle these effects. Individuals don't really differ in abdomen by 1 centimeter. They're differing in other things simultaneously. And so the regression model, it's doing its best. It's trying to imagine a world where, yes, we can find these individuals that differ in abdomen circumference by 1 centimeter, but nothing else. But the data doesn't really bear that out, so it's having to make kind of a bit of guesswork to see what those two individuals would really look like. And that extra guesswork is degrading that precision of our estimated coefficient. So, long story short,
And to make a long story short, too late!
if there's a lot of correlation among the predictors you're using in your multiple linear regression model, the precision of those estimated coefficients gets degraded. The standard errors of those coefficients gets larger. It gets harder and harder to nail down really how the y values of two individuals are going to differ when they differ in x by just that one unit, when they're expected to differ in all these other characteristics simultaneously. So we can gauge how much of an effect this correlation has on our model by looking at what's known as the variance inflation factors of the coefficients. If I, after I fit a model, type out VIF and put my model in there, it lets me know how much the correlation between the different predictors has affected the precision of my estimated coefficients. So abdomen right here gets a variance inflation factor of 11.77. If I were to take the square root of this lets me know the factor by which the standard error has increased due to correlation between abdomen and these other predictors. So it's letting me know that the standard error of the abdomen coefficient in my model is about 3.4 times larger than it would have been if every single one of these predictors was independent of one another. They're all sharing information about body fat percentage in these measurements, but there's so much redundancy flying around, it's hard for us to separate out really what can be attributable to abdomen circumference alone. Now, how large does the variance inflation factor have to be in order for us to start getting worried about the precision of our estimated coefficients? Well, surprisingly, there's no hard and fast rule. Very often, if you open up a textbook, they'll say, hey, if you see a variance inflation factor of around 5 or 10, then that means the model is having trouble estimating the coefficient of that predictor variable. But I have another guideline that I seem to like a little bit better. So let's go and actually fit that body fat example one more time, predicting body fat percentage from everything that we have available. And let's look at the R-squared of the model. So in this case, using our model gets us about 74.9% of the way there to knowing someone's body fat percentage. So pretty decent model actually for making predictions. What I'm going to do is I'm going to calculate the quantity 1 divided by 1 minus R-squared. And I'm going to use this as a threshold to compare the variance inflation factors to. So printing out those variance inflation factors and printing out that threshold one more time, I'm looking for any variance inflation factors that are bigger than 4. So why do you see those pretty much all over the place? Neck, chest, abdomen, hip, etc. So why does this threshold make sense? Well, let's look at the variance inflation factor of abdomen one more time at about 11.8. Because that's larger than the threshold of 4, essentially all the other predictors in the model are actually predicting abdomen better than they're predicting the body fat percentage. So if your other predictors are predicting an X variable better than it's at predicting the Y variable, then that's kind of an issue. And that's a signal to me that, hey, the model's having difficulty trying to estimate the coefficients of the predictor variable. So bigger than 5, bigger than 10, kind of a red flag, or bigger than that 1 divided by 1 minus R-squared, all pretty good thresholds for determining when this intravariable correlation is an issue. And we have a special name for this if we do have a lot of predictors suffering from high correlations. We say that if we have a bunch of these predictors having large VIFs, that the model suffers from multicollinearity. So multicollinearity just means that a lot of these predictor variables are correlated. The model's going to have a hard time disentangling the effects of each predictor variable on the Y variable from each other. So the consequences of a model being fraught with multicollinearity just means that the model's having trouble estimating those coefficients. If you're doing descriptive analytics, you have your work cut out for you because there aren't really individuals that differ in X by just 1 unit and that are identical otherwise, since these predictor variables are changing simultaneously with their correlations. So multicollinearity indicates to us that, okay, the coefficients of the predictors aren't being well estimated, but the key thing is that the presence of multicollinearity doesn't invalidate the model. The model's still good, it's just having issues estimating those coefficients with nice precision. And even better, actually, if we're going to be using our model for doing predictive analytics, it turns out that multicollinearity really doesn't have that much of an effect on the predictive value of the model. So when we do see large VIFs, we just know that, all right, the model's having a hard time estimating those coefficients. The predictions will still be pretty good, but trying to interpret those coefficients might be a bit on the tricky side.